Hello. Oh, hello. This is a quick video that one or two students asked for as a quick review of the Truncus function. So looking at the equation and going through a couple of work examples pretty quickly. So that's what we're going to do here. This isn't designed as a full teaching video so much as a quick overview of the core concepts. So we'll jump straight into it. So the Truncus we looked at after we looked at the hyperbola. So the hyperbola, the very most basic version of it is y equals 1 on x. And in this case, we're now going to move to something that looks very, very similar, but we get y equals 1 on x squared. And the same idea, let's put some values in, see what outputs we get or what results we get from the function, and then make some conclusions from that. So if I put -4 in, I get 1 on 16. If I put -2 in, I get 1 on 4. -1 in, I get 1 on 1, so just 1. If I put -½ in, I end up getting 4. And same if I put half in, I get 1. Get 1/4, and I get 1 over 16. Just to quickly show sort of how we get the 4 from this is we get y equals 1 on -½ all squared, which gives me 1 on that fraction squared becomes a quarter. Okay. Now we have 1 divided by a quarter, and if we remember, if we're ever dividing by a fraction, what we actually do is we can multiply by the reciprocal instead. So instead of 1 divided by a quarter, we can do 1 times by 4 over 1, and that gives us 4 finally. So that's where that 4 comes from. Couple things to note here. One, we'll look at the similarity with the hyperbola. Okay. As our x value gets larger, the denominator of the actual function gets larger, okay, because we're putting our x value into the denominator. So as our x value gets larger, our denominator gets larger. So if we think of this, the whole thing as a number, our whole number, our output, gets smaller. So as x gets larger, y gets smaller. So that's very similar to hyperbola. And if we think of the basic graph of that, as our x gets larger, our y is going to get smaller, and we get that sort of shape. Okay. Being a square under here, so in this case, this effect is even more pronounced than a hyperbola. So with a hyperbola, we might get that sort of shape. For the Truncus, I might use a green line instead. The shape is much more pronounced. Much more pronounced. Yeah. The difference, though, is the square. Okay. What impact that has when x is negative? Well, when x value is negative, because it's squared, it's now becoming positive. Okay, so all our y values, even though x is negative, y in this case stays positive, but with that same pattern. So instead of being down over here, we get that going on. So my kitten is just saying hi. Unlike the hyperbola, where we would consider it quickly up in this graph, this red line, a truncus is actually looks like a trunk of a tree, and that's how I remember what it is. Squared means it forces all values positive, and therefore our two lines are actually going up and gives the shape of a trunk. Right, so if we sketch those values from the previous slide, we would get 1, 1, 2 gave me a quarter, 4 gave me 1/16, so very, very tiny. There, half gave me 4. There. We connect the dots. We get that. And same over on this side. So we get this sort of shape. Now, to just be clear, the differences, I was a little bit incorrect in my difference from the hyperbola and the shape of the line. A hyperbola still goes through 1, 1, but when it's half, the y value is 2. There, get that sort of shape. So they're similar. It's, yeah, the truncus really gets pulled down in this zone here. Okay? And also then gets really tall really quickly. So I guess when the hyperbola has probably a nice, smooth, consistent curve, while the truncus has got this very ramps up sort of shape, and they both go through 1, 1 in the most basic form. That's to sort of identify the differences. Just like with the hyperbola, we can write it as what we consider the general form, where A is our dilation factor, H turns out to give us a horizontal translation, and K gives us a vertical translation. We still also have, I should have noted, we still have asymptotes. Straight out. We still have asymptotes, just like the hyperbola. Okay. This x squared, we're never allowed to divide by 0. Okay. We're never allowed that. So in this case, our hyperbola, our truncus has an asymptote at x equals 0. We're never putting in that. And because of that, we can never get our y value also to be 0. So we have an asymptote at y equals 0. So that's note. So when we start translating in this general form here, just like with the hyperbola, think of moving the whole thing left, right, or up and down. And we'll look at some examples. So on the axis below, sketch the graph of y equals 1 on x squared minus 2, labeling the intercepts equations for the asymptotes and a point of reference if appropriate. So the very first thing I look for is the h and k value. If we want to graph this efficiently, we want to note what it is. Now this has nothing in here in the squared. It doesn't have the h there. So in our case, h is 0, so there's no horizontal translation, and our k is -2. So the first things I do is then I just graph in that asymptote straight away. I know there's going to be one at x equals 0, because my h value is 0, and k is -2, so my whole graph is being pulled down 2 units. I can put that in as y equals -2. So we have that. Roughly, just to have an idea if there'll be intercepts that exist, I would recommend just putting in some rough lines in grey lead straight away, so I can see, well, there's going to be an intercept there and there's going to be an intercept there, but also recognize, because of my asymptote, there's no y-intercept. So you're not going to be able to find one. I see a lot of people in tests making that mistake. They're trying to find y-intercepts, when if they just put in the lines roughly in grey lead, which we're going to go back and correct with correct values, there'll be no intercept there. So let's find our x-intercepts. So to find the x-intercept, we're going to let y equals 0. So we get 0 equals 1 on x squared minus 2. Take the 2 over, we get 1 on x squared. Multiply both sides by x squared, so we get 2x squared is 1. Now I'm going to divide both sides by 2 to get the x squared by itself, so we get half. So x is equal to the square root of half. And it's going to be plus or minus when we take the square root of both sides. So that's all that we're left with. X is equal to the square root of half plus or minus. What is that roughly as a decimal? Taking the square root of half, we could, if you wanted to, you could break that down as the square root of 1 divided by the square root of 2. That's plus or minus that. Well, square root of 1 is 1. And square root of 2 is roughly 1 point something. So we've got 1 divided by 1 point something, which means it's going to be less than 1. So if I can remember off the top of my head, it's about 0.7. So we get plus or minus that. So we can put that in. That is 1 on root 2 comma 0, and over this side we have negative 1 on root 2 comma 0. The lines come down. Something like that. Yeah. Need to put our arrows on at the end. A careful thing with sketching, just like the hyperbola, we need to have our lines showing that they're going towards the asymptotes. Some people, I've overpronounced that, but some people will come up and do that. And that's going away. That's no longer approaching the asymptote, so that's incorrect. You need to finish your line going towards the asymptote, just gradually going towards the asymptote. Since we have intercepts on both of our lines have a key point on it that we've identified with a coordinate, we don't need a point of reference in this case. Rightio, same thing again. On the x below, sketch graph of y equals 2 on x minus 1 all squared minus 2. Label intercepts, equations for the asymptotes, and point of reference as need be. So straight away looking at this, I can see h is equal to 1, switching the sign for h, k is equal to negative 2. So I'm going to put my asymptotes in straight away. Since h is 1, the asymptote is moved over to 1. So that's x equals 1, and y is equal to negative 2. I'm going to put that in there. Y is equal to negative 2. Again, I'm going to sketch in a really rough line, something like that, something like that. Okay. So straight away, I can see there's going to be a y-intercept and an x-intercept somewhere there, somewhere. It could even be coming through like that, but there's going to be something. And then there's also an x-intercept over here. So in this case, I need to find both the x-intercept and the y-intercept. So let's find our y-intercept first. Generally, that's easier, letting x equal 0. So I'm going to find my y-intercept. So I'm going to let x equal to 0. So I get y is equal to 2 on x, 0 minus 1 all squared minus 2. So I get y is equal to 2 on 1, because negative 1 all squared is 1, minus 2. So I get 2 take away 2, which is equal to 0. It turns out my y-intercept is there at 0, 0. So my line's coming through. That's also given us the x-intercept. It's it's a very rare occurrence this occurs, but on this side we can see that it goes through 0, 0. So that's our x-intercept and y-intercept all in one go. But we still need to find the other x-intercept over this side. If you switched on, a truncus is symmetrical about the asymptote. So if we realize that this one is across 1 unit, we can also realize this is across 1 unit, and straight away we get our other intercept coming down. So we could get something like that. But let's do the maths to actually find this one here on the right. So for our x-intercepts, we let y equal to 0. So we get 0 is equal to 2 on x minus 2 all squared minus 2. We eventually want to get the x by itself, but we're going to have to move some stuff away from it. I apologise if there's some background rustling noise. It's my cat playing with a plastic bag now. So we take the negative 2 across, so we get 2 is equal to 2 on x minus 2 all squared. I'm going to multiply both sides by that x minus 2 all squared, so I get 2 x minus 2 all squared is equal to 2. Now I'm going to divide both sides by 2 to get rid of that one in the front. I'm now left with x minus 2 all squared is equal to 1. Square root both sides, so we get x minus 2 is equal to plus or minus the square root of 1. I get x is equal to plus or minus the square root of 1 plus 2. Square root of 1 is just 1, so I get plus or minus 1 plus 2. So if I take the have I done something wrong here? This shouldn't be. Where did I put a 2 in there? Okay. This whole time that was a 1 inside the brackets. 1, 1, 1, 1. Yeah, so that's yes. Now, plus or minus 1, plus 1. So if we take the positive 1 to start with, that's 1 plus 1 gives me 2. If I take the negative 1, I get negative 1 plus 1, which is equal to 0. So that gives me my 2, 0, and it also gives me my 0, 0. So it finds the one on the left-hand side as well. Rightio, last one. Now, since this is a negative here, just like a hyperbola, if our dilation is also a negative, that means it's reflecting. Okay, it's making, we're putting in, the way I think of it is we're putting in an x value, whatever it is, we're doing some operations to it, we eventually get a number. If we ignore the negative was there, imagine it's out the front, which we can. Okay, all of this gives me a number, which is going to be positive no matter what because of that squared. We're then taking that positive number and making it negative because of the negative in front of that 1, which we've now taken out the front. So no matter what happens, we put in an x value, do some stuff to it, and then all of a sudden we're then making it negative. So that reflects at everything. Whatever we're getting before, we're getting it, but we just made the y value negative. So we actually get inverted Truncus, just like a hyperbola where it flips everything. We get that as well for a Truncus. So if you ever see that negative in front up there, it's reflecting the Truncus over. So straight away, look at the x value there. My h is -2. And in this case, I've got no k value, so k is equal to 0. So I'm going to put those in straight away. Y is equal to 0 as that asymptote, and x is equal to -2 in this case. And I'm going to put in my rough sketch and see over here, that one has no intercepts at all. And this one does have a y-intercept. So this is that case, if you went and tried to find an x-intercept, it would be impossible because that's where the asymptote is. And you'll run into some maths that you can't do. Which will generally be taking the square root of a negative. So if you run into it, you ever try and take the square root of a negative, probably means you're trying to find an intercept that doesn't exist. But we do have this y-intercept that we need to find. So for the y-intercept, we let x equal to 0, so we get y is equal to -1 on 3 by 0 plus 2 all squared is equal to -1 on 3 by 4. So we get -1 on 12. So that's a pretty small number. So that is going to be about, actually it's going to be really close to the axis. So let me fix up the asymptote a bit there. We're going to go through about there. That will roughly do for scale. So we get 0, -1 12th point there. And there's my right hand side. Now the left hand side is going to be symmetrical about that. So if I think that's 2 units across from the asymptote, 2 units back across, that's going to be the exact same point. Just 2 units back across from the asymptote, which is already at -2. So that's going to be at -4, -1 12th. It's going to go through that point there. Now again, if you're not good at recognizing the symmetrical nature, and this is a case where you need a point of reference, the line on the right, the right hand side of the Truncus has an intercept like the side on the left, so we need a point of reference. If you weren't good at recognizing the symmetry, all you do is just pick any x value on that left hand side. You could choose x equals -3, you could choose x equals -4, any one, sub it in and get your point of reference. So we'll just do that quickly just for practice. Point of reference, I'm going to choose x equals -3 just for something different. I'm going to let x equals -3, so I get y is equal to -1 on 3 by -3 plus 2 all squared, -1 on 3 by -1 all squared. -1 squared is 1, so we just get -1 over 3, 1/3. So means it's actually about there. My point of reference, that is -3, 1/3. If I fix up my line, actually does something like that, and so I should probably fix up my right hand side as well. And just for symmetry, there we go. And there's the truncus. Last but not least is, I guess it's sort of a hidden truncus, a bit like a hidden hyperbola. Is we can only read our H value, and our trick for being most efficient, and that's what we're working towards. I hate to say it, but come the Year 12 exam is you just need to be efficient and quick. To be the most efficient is read that H, read the K value, stick the asymptotes in. If our X has any coefficient, be it a minus sign inside that bracket, be a number, anything, if it has a coefficient, anything other than 1, you need to take that outside. You need to get it out. Now, there's two ways you can do it. Way 1, which is over here, and then way 2 is over here. Way 1 is expand out this. You're then going to get a quadratic, which you then need to take the common factor out, and then refactorize what's left of the quadratic, and then you get something like this. The other way is you could just take out that, whatever the number is in front here, take that as a common factor, but keep it inside the square, because technically it's still in there. And then using index laws, you can take it outside the bracket, because in this case we have 2x plus 3 all squared. That is actually the same as 1 on, and using our index laws, which say if we had a times by b, and that's all squared, that's the same as a squared times by b squared. In this case, that bit there is our a, and this bit there is our b, because it's 2 times by that whole term in the brackets, or expression in the brackets. That's the same as 2 squared bracket x plus 3 all squared. Do the 2 squared, that gives us our 4. And we can now read our h value properly as 3. So, to read the h value, to reiterate, if there is any coefficient in front of the x inside the brackets, you must get that outside. I suggest this alternative way is generally the... I suggest that alternative method. Rightio. So there's an example of it. Is taking that 3 out, we need to get rid of because the x has got a coefficient. So I could write this instead as 1 on 3 bracket. The 3's all squared, x plus, since we're taking 4 out, all squared. So we get y is equal to 1 on 9. All squared. So we can read, in this case, our h value is actually -4. So we can say it is translated in the direction of the negative x-axis by 4 units. CAS, that's for the CAS that we don't use, unfortunately. So we don't quite have that shortcut, unfortunately. That's it for the truncus. A little long, sorry to the people that request this, but I hope that's everything you needed.